upperclassmen talked about the complex technical areas of work being done, I felt completely overwhelmed by the complicated engineering work. And as my family definitely feels when I go about speaking about IrishSat, and you might tonight, I just still had an irresistible urge to return. The fun, welcoming, intense, goofy, technical, friendly, eclectic environment was exactly what I had not known that I needed. And now that's what I try to foster here every single day. Through mentorship, friendship, experience, trust, patience, teaching, and the building up of my role within the club, I was able to transform myself day by day. Upperclassmen on IrishSat take young engineers under their wing and make a point of maintaining a close relationship and being a mentor and a friend as they grow up and grow into their engineering skills. Our older teammates push us to learn and to grow. They take us out of our comfort zone while also making us feel more and more comfortable every meeting. Because of IrishSat, I not only became a stronger leader and engineer, but a more confident person, a more joyful person, and a person who actually looks forward to what each new day brings. Being on IrishSat allows you to approach every new day with a unique and fun, new meaningful challenge. Each day has the opportunity for success, and our small victories always mean the world. I'm just so proud every single day of what my team accomplishes. Nothing warms my heart more than witnessing transformations like my own as freshmen blossom into strong forces within our club. We get to build up this family of people with like-minded passions and a genuine care for one another. Every day I work with and just look at this team of brilliant engineers and young minds, and I guffaw at the fact that I've been trusted with their leadership now. Technically and socially, our teammates always come to myself or each other's side in order to be there and build each other up. We all want to see each other grow and succeed, and the collaborative, supportive family that we have is what makes us so successful, both in our team endeavors and individually. Sometimes I think that I exaggerate, and IrishSat is really not that big of a deal. But then I think about my own story and how much a life can change just by joining a little club, as well as the great feats that we're able to accomplish together. It can be hard to explain why I've dedicated my college years to this, but I have absolutely no regrets about the time that I've spent in our workshop as I try to emulate the leadership that helped me to evolve into the person I am today. I cannot wait to continue to foster more generations of young engineers who are happy, confident, successful, and passionate for everyday life, and able to partake in the bite-sized victories that make our team thrive. Thank you so much for either being a part of IrishSat or supporting those who are. Now I would like to hand it off to Juwan so they can hear more about what our members are actually involved in that allows them to do all of this. Thank you.
Strong speech, just follow us up. Do my best. Can you hear me? My voice not clear. Oh, a little louder? A little louder. Okay, cool. Hey everyone, my name is Juwan. I'm a graduating senior, and I'm the outgoing director of research and development for IrishSat, of which I've been the director of R&D for the past few years. Yeah, and again, Sarah and Luke have already said it pretty well. But again, I just want to thank you guys so much for taking the time to travel and to visit and to sit down and gather at this banquet. This is really kind of the reason why we do this, just to see kind of everyone gather to see what everyone has done. So thank you so much. Without this, I don't think it'd be IrishSat would be half as great. And I guess for the past 2 years, that's something I've really learned, that seeing all the people who come to support us in different ways, whether that's emotional support to make sure we don't break down crying because these problems are so hard, whether that's technical guidance to make sure that we can solve these problems in the first place. I think it's great to see so many people help us in different ways. And that's what makes IrishSat really special. That's something I think I realized a lot last semester, which is when we wrote our first CSLI proposal, which is something Luke mentioned earlier. So for people who don't know, the NASA CSLI program is a program that invites undergraduate teams to submit a proposal for a CubeSat mission, and if they like their mission, they're gonna give you a free ride to space. So basically, you give them a CubeSat, that CubeSat is going to space. And when I first joined the club, that was kind of the hook to it. It was like, we're gonna do a CubeSat and it's gonna go into space. And I was just so amazed that this is something undergraduates could do. But both in my sophomore year and junior year, that didn't happen yet. So I was really excited to be able to be the lead proposal writer for the CSLI proposal of IrishSat this year. So the past year, we worked with Dr. Chisholm to integrate his research on these novel antennas and put it into a satellite. And it's been great really working with him to make this proposal. And I don't know, just throughout the process, I was really amazed by seeing the collaboration going on in the team and outside of the team. In the team, I can just rave and rant about like how much people helped. Everyone helped in this proposal. It wasn't just me, it was every project lead, practically every member, everything that we're doing was contributing to this proposal. And through some pretty late nights, they were really helpful in getting this done for the deadline. And the mentors, it's really fantastic to see how much they helped us. If I showed you guys like the first draft of the proposal, I would like run out crying and shit because it's really messy. But they gave us some pretty strong feedback to make it a very serviceable, well-crafted, and strong proposal. I remember this one email that Professor Chisholm gave us. Like, we showed him the draft, he gave us feedback, and then we fixed it, and he said, it has come a long way. And I don't know why, but it just stuck with me, like him giving that feedback of how much it shaped in the past few years. So again, I would like to thank Dr. Chisholm for helping us with getting this proposal on the ground. I also want to thank Dr. Howard because he's our club advisor and he's helped us in many different ways. And also the countless professors who we bother every week asking about questions of, oh, we can't do this, how do we do it? And they're always so willing to meet with us and work the problem through. And it would be rude of me to not mention the industry contacts, the many countless industry contacts we have from different companies. Isaac and Patrick can tell you more about that. But last year, they were so great in getting this proposal process getting through. I remember last week, there was 1 week during fall break where we met for 3 hours with a bunch of Boeing engineers going over the proposal. And they were just giving us very strong feedback just throughout this meeting. And it was great to see that. And it's been a privilege to be able to be the one to facilitate this. I feel like it's been really instrumental to my growth as just a person, professionally and personally. Well, I do have to bring the bad news that our proposal didn't get accepted this year. This is only our first proposal. We have many other tries coming this coming year. And ever since we found out our decision, we've been getting good feedback to make it stronger, been thinking of ways to make it more palatable to NASA. So it's a privilege to be able to be the first one to do this, but I'm more excited to see what the next year's leadership can do. I know they can do better than me, and with your support as mentors, you guys will do great. We'll get the proposal. So thank you. So now we're going to talk about the logistics of how we're going to do demos. So we're going to try to split up to 4 different groups. So there's 4 rooms we're running the demos. One, which is our instrumentation lab. There's one, which is our CubeSat team. And then up there, in the second floor in 212, 213, the room is split up, so it's 212, 213. One of them is ground station together with the comms team. And one of them is IRIS, or High Altitude Balloon Mission, together with Starshade, win their NASA competition. So we're going to try to split up to 4 different groups.
The plates on the sides.
Was that?
The trashes are on the side of the room.
Oh yeah, so there's trash inside the room. And also for people who need to get up, like they can't take the stairs, there's an elevator down this hallway to the left.
And I cut the cake, so please eat the cake.
So yeah, we're just gonna split up to 4 different groups.
Take this table, half this table.
Yeah, let's do half of this table goes.
Well, there's a lot of people, students here, so why don't we just have people kind of disperse?
Yeah, how about the students go to your shirts?
There are 4 people in the chat. Dude, how is it still? Oh yeah, sure. Oh, you know what? Yeah, I'll move the camera. We're gonna start here. Yeah. Oh, you're presenting first. Yeah, this first. I don't know. I would still actually probably unplug from the wall before I do that. I realized I've left it running this entire time. Hello, Tyler. Hello, Will. The world can hear you right now. Oh, wait, am I on live stream? Yeah. Hello. I don't know.
Have you guys seen Will?
Oh, yeah. That doesn't actually do anything. It was this thing the whole time. Oh, my God. This thing's fun, though.
Juwan, I'm sorry. Exactly.
That I brought up IrishSat to in my last.
Yeah. Oh, Nicholas. Adrian.
I friend
Who's that? He's at a conference.
Are you passing my resume, by the way? I did know that. Oh, wait.
Also, the audio just on because I'm scared of muting it again because every time I'm muting it, it's broken.
Is the mini mic working?
Yeah.
Oh, are we using the mini mic?
Huh?
Are we using the mini mic?
No, not the mini mic, the parabolic mic right here.
Okay, cool.
Yeah.
Oh, yeah, no ASMR. Sounds good.
All right. There we get started. Oh, we're really?
I don't know.
Alright, you know, hey guys, we need to move all to these tables at the same time. Don't like all table function together. Are you gonna like pivot the camera? Yeah. Okay. Pretty cool. Ready, watch this. Ready. Oh.
Awesome.
Oh,
okay. Hi everyone, my name is Ariana. I'm a junior studying aerospace engineering, and I'm the chief structural engineer of GoLab.
I'm Tyler. I'm a sophomore electrical engineer, and I'm the chief electrical engineer of GoLab.
So GoLab stands for Gravitational Orbital Attitude Thermal Lab, and we are responsible for the development of satellite testing instrumentation to analyze different satellite subsystems and prototypes of Notre Dame's first ever satellite. So this year we have 5 new projects to present to you, and my talented team of engineers is going to go through each one and talk about the design, the construction, and how we made it. So beginning with our vibration table. Our vibration table is used to assess flight readiness. So when a satellite goes up into space, it's experiencing a lot of vibrational shocks and forces. So if we're able to replicate those forces, we can ensure that our satellite is structurally sound enough to make it up to space. So presenting will be Johnny, Salvi, Joe, and Brady.
Hi everyone, I'm John Tuma. I am IrishSat's manufacturing technical lead. So I've dipped my toes into all of these projects, but today I would be presenting to you the vibration tables. So as already mentioned, we need to be able to test that our satellites are able to withstand the forces experienced during launch. So in order to do that, we want to test our satellites through a certain range of vibrational frequencies. And NASA provides a table that has the frequency versus the power spectral density of the force experienced by the satellite, and that'll be touched upon in more detail later. But essentially what we do is we measure with using an accelerometer how fast our satellite is moving from the vibrations on the table. So we have several iterations here, and I will let Joe begin with the first.
So my name's Joe, and this is our first prototype of the vibration table. I want to make it something cheap and quick. So made out of wood. It's a very available material. And we initially made it with a 3U box. That's why it's a lot longer in this guy. We weren't sure at this point whether our CubeSat was going to be the 2U length like that or the full 3U, which this is designed for. And so we were able to use a DC offset motor to create the vibrations on here. And with this rig, we're able to reach about 20 to 50 hertz, which is definitely on the way lower side of the vibrations we need. But it was a good proof of concept that we could do it. And there's a lot of things that we took from it that worked and that didn't work that we put into our next iteration.
Hey everyone, my name is David. I'm a mechanical engineering freshman, originally from Brazil. And I'll be talking about our new iteration. So basically we saw what went right with the first one, and we developed a lighter and more durable version. So instead of using wood, we used an aluminum sheet as the base and acrylic panels as the frames that will keep the CubeSat in place. Another very interesting feature of this new vibration table is that we can change the direction. So we can move this whole thing to the horizontal, and we can test the vibration on the horizontal direction. And last but not least, a very important aspect of this new vibration table is the motor. So for this one, we're using a 2-head offset DC motor. And that means that we, instead of having one offset weight, we have 2 offset weights in this one. And another very important measurement of this new motor is that the maximum angular velocity is also higher. And so we estimate that the frequency of this new vibration table ranges from 200 to 500 hertz, demonstrating the effectiveness of this new iteration. I'll let Bernie now talk about the accelerometer and why this is such an important feature.
So I'm Bernie, I'm a freshman electrical engineer, and the accelerometer itself is comprised of a microprocessor and a sensor. The sensor detects acceleration, and then we transform it into frequency. The frequency is important because it's what denotes the actual vibrations, which we can use to compare to NASA's table. Now we will present a short demo on the table.
So when we turn this on, this table is going to start vibrating, and essentially this CubeSat would be moving with the same vibrations, and the accelerometer on top would be reading what the forces that it experiences. So if we adjust the voltage, the higher voltage, the faster it vibrates. So we're able to test a wide range of frequencies. And in the future, we're going to be improving upon these designs to try and reach those higher frequencies that we want to hit.
All right. So our next project is our flat plate air bearing. Making way. So our flat plate air bearing design is used for one-axis flywheel testing. And so a flywheel is also called a reaction wheel. You'll probably hear the other team say stuff about it too. But basically, it controls the orientation of our satellite in space. And so in order to test that those components are working properly and our signals and transmissions are working well, we developed a flat plate air bearing. Talking about the flat plate air bearing is Carla, Madeline, and Oriana.
Hi, my name is Carla Salgado. I am an aerospace engineering major. So for our flat plate air bearing design, we have a square base with a mounting top with 316 holes. The base also has 2 input valves on each side where we can insert the shop vacuums with blowing features, each one blowing at 65 CFMs. And on the inside, there's also a 3D printed pipe that goes all the way through the center.
Hi, I'm Madeline, and I'm a freshman physics major. And the pipe in the center is for stability, and it allows us to rotate along the z-axis. And the flat plate air bearing table basically functions as an air hockey table, where when we blow the air up, it creates an air pocket underneath the test plate, and that allows it to have quasi-frictionless rotation.
Hi, I'm Mariana Sade. I'm a freshman in aerospace engineering, and for the manufacturing of it, we laser coated the melamine and the base of the table. We also rubbed the inside of the table to reduce airflow, and we 3D printed other features of the project, such as the tubing, the bag that is below the disc, and the pipe that is inside of the. So I will present a quick demo.
So when we turn on the vacuums, it's just going to blow air through the table, and we should be able to spin it so that it's frictionless.
Our third project is our gimbal suspension ADCS test rig. Super technically long name for it, but our gimbal suspension test rig is meant to simulate the tumbling aspect of our satellite deployment. So when a satellite is launched into space, it's ejected via something called an orbital deployer, which simplified down is basically a box with a spring. So when it's launched into space, it gets thrown in, and with no friction in space, it'll spin and tumble without anything to stop it unless we initiate some sort of force on it. And that's what our reaction wheels and our magnetors do. So presenting our gimbal ADCS system is Micheline and Adele.
Hi, I'm Adele. I'm a sophomore aerospace engineering student. So this was our first iteration of the gimbal. This is what we did last semester. So we were wanting to see if we could do a multi-axis testing device in order to see if the flywheels on the satellite would work. So while this was one axis, this is going to be multiple. So we decided to start with 2 rings as a proof of concept. We decided to go with square ones because they were easy to build at the time. And we saw that it could spin and it would work. And we also played around with the satellite mounting system.
Yeah, so after this iteration, we decided to make a new one to make a more robust design. And as you can see, there are a few differences. The main one being that this has circular rings and this one has square ones. This is because when we wanted to test the CubeSat, we want to have the least amount of forces reacting with the CubeSat from the gimbal itself. And for that reason, we use circular rings because they have a lower moment of inertia or a lower resistance to rotation. And then as you can see, we also have 3 rings here. And we drilled holes into them to make sure that it was lighter, which also helps with the forces acting on the satellite. So the idea is that, like you can see in the first iteration, we would clamp the satellite into this, and as you can see, it would spin. And the reaction wheels that we've been talking about would be able to slow the spinning and even stop it, or even make the satellite turn in different directions.
All right, everyone, our fourth and final project is the Helmholtz cage in our encoder unit, which Tyler and Brandy are going to talk.
So beginning with the encoder unit, we have a first prototype here, which has 2 encoders, one on the X and one on the Y axes, which are used to detect how much the gimbal rotates. This is done by using a sensor and a rotor, which counts how much the rotor is turning and converts that to degrees. In the future, we're going to try and make the design smaller using PCBs, and these are going to be used to get data to the computing team so they can improve their simulations in the future.
And to improve that same simulation even more, we have the Helmholtz cage, which consists of 6 coils of wire which we run electricity through to generate magnetic fields in the middle. This circuit allows us to control the level of magnetic field that we get. So if you look at the monitor, we can increase or decrease each magnetic field in the directions that we want. Using this, we can simulate the magnetic forces that a satellite will experience within Earth's orbit, and we can test the effects of that same magnetic field on a magnetorquer and a magnetometer. In the future, we would like to turn this mangle of wires into a PCB and greatly shrink the encoder so we can have a bigger gimbal.
Okay, and lastly, I'd like to invite Elena to speak on our next steps in the future of GoLab.
Hi everyone, I'm Elena Sayas. I'm a sophomore aerospace engineering student, and
I'm happy to announce that I'll be filling in for Ariana's position next year as the Chief Engineer of GoatLab Structures. So I thought it'd be fitting to talk about our next steps as a club. So the first thing we definitely want to iterate on is the vibration table. We want to utilize acoustics next time to increase the frequency of the vibrations, because obviously the higher the frequency, the better, so that we can really simulate the rocket launch and how the satellite withstands that shaking. And then we also want to iterate on the three-dimensional gimbal design. Right now, there's a lot of friction in the ball bearings, which is what makes it spin. So we want to reduce that, and we also want to reduce the amount of weight on the ring, because those two factors will create faster spinning, and it will spin for longer, which is the goal. And then a new project we definitely want to work on next year is creating a thermal test environment in order to test the extreme temperatures in space and see if our satellite can withstand that. So I'm very excited to fill in for Ariana's position. She left me some big shoes to fill. But I appreciate you all for coming to this presentation. It really means a lot to us.
Questions? Remember, that's the next place.
Sorry?
Yeah, they go upstairs.
We are now going to
Process that signal, and we'll understand, okay, this is the command we can make this adjustment to our orientation. So this is kind of a very of like ground station, satellite, this is how they're. Yeah. Any other questions? Okay.
Any questions for us? Were you guys able to recreate the satellite tracking that you guys got last year?
So we actually were able to do that. So we were using a program, it was proprietary, called Ham Radio Deluxe, and we weren't pleased with it last year. So we restarted with I reached out to other university ground stations, and due to advice from like Stanford and Cal Polytechnic, we switched over to something called GPredict, which is open source and is used by their ground stations to track their satellites who are currently in orbit. Yeah.
Awesome.
Yeah. If we go to the other presentation, I was using that, and
we're still working out some bugs in getting the SDRs connected. But this is using a thumb drive SDR, so not one that can use the main antenna with the rotor. This is just a really simplistic SDR, but these are telemetry from NOAA weather satellites that I was able to download last night.
Using which SDR now? The US
No, we had we had an issue because our antenna uses a different sized aux cable. And then we didn't have male to female connectors.
Amazon.
Yeah. So we had some issues. We're still ironing out some bugs. We had to get the rotor controller also
Ours
fixed.
is impressive that you guys got back up to the level of knowledge that was had before all the people. And same for ComSteam.
And so, basically the satellite tracking software, what it was doing, because it wasn't controlling the rotor, was it was managing Doppler shift. So it was changing the frequency as the satellite went overhead.
For context, communication stuff is typically learned like senior year of college. So it's really impressive that these kids being the years of school they're in have managed to pick up all this stuff.
All done? All right, well, you guys can, the group next door has no one right now, so if you guys want to hear about our altitude balloon project and Starshade, both of them won NASA competitions this year, so that's very exciting. And they're with you guys over next door, so you just go out, left, and left again, just kind of around this makeshift wall. Thank you.
Good job.
Thank you. All right. Notes. When you heard
Is there a quiz later?
Yeah, there is. Yeah. So you guys are screwed. Yeah. ESC, Electronic Church.
Okay.
This would be electronic.
Okay.
Tips. So we have a very family and friends type crowd. So talking super technical, which is what we wrote up. Yeah, is not working.
Okay, yeah.
So we need to go higher level with it. Where are my notes?
Like, oh.
Your speech. My speech.
Oh, is it?
There's a paper here.
Nice.
Is there another group coming? Yeah. So yeah.
Should I use a different?
Oh boy, we got the rowdy crew this time.
Woo! Was the last crew not? We're gonna break something. I was up front and center. Oh, you guys are
Yeah.
Why is this
Yeah. Alrighty, you guys ready? Have your socks blown off. All right, ground station is going to go first, and then we have the communications technical group here. Pretty related, we work together often, so you guys can take it away.
Hello, I'm Sean Kurth. I am the leader of Ground Station. So Ground Station's been a project with the IrishSat for the last 2 or 3 years. It was kickstarted by our founding members. Basically, they said, you know, if we're going to put a satellite in orbit, we're going to need something to talk to it, and we want to have it working before it gets into orbit. So they wrote a proposal to the Department of Physics, and they got permission to put it up on the roof of Newland.
according to the chairman of the electrical engineering department, this is the pretty cloth, so they can't put it up here. We have to put it elsewhere so you can't see it from the roof. That's why it's on the roof Newland, which is about a quarter mile, maybe less from here. I'm bad with distance. And so that year they worked on the superstructure you can see here, which holds up the rotor and the antennas. And then last year, my first year with ground station, we worked on through struggles because the rotor came in broken. We worked on actually getting the antennas put on and starting with the basics of tracking satellites. So by the end of last year, this picture was taken in spring last year. By the end of last year, we were able to track satellites minorly and downlink from them. Unfortunately, at the end of last year as well, we lost most of our experienced senior members who are also double-E's. So I and Isaac, the last two left, I became the lead of ground station, and I'm an aerospace engineer major, so I'm not super versed in this. But I've worked hard, I've grown the team, we're trying to reawaken ground station. This year I have 2 CPEG freshmen, a CPEG junior, and a double E sophomore, as well as myself, to work on this project. I'm very proud of us. So basically, we were it's a learning curve. None of us know much because we haven't taken the classes yet. We've had to learn a lot because we're trying to shift to a more operations standpoint as well. So we want everyone to be able to control the satellite. It was mandatory for every team member to get their ham radio license.
Yes. To operate well, first I'm Kyle. I'm one of the CPEG freshmen that joined the team this year. And as John was saying, one of the mandatory things for us to operate the ground station is that we need to be legally certified to do that. So because of that, last semester during the fall, the entire team worked through a ham radio guide that we got from one of the professors from the department here at Notre Dame. And we basically spent most of the semester just working through the guide and learning all the concepts, just like it was if it was like another class we're taking. And with that, we were able to successfully, at the end of the semester, to get everyone tested and everyone got their technician level ham radio licenses. So now we're all certified to transmit radio signals through the ground station. And then for this semester, the computer engineers of the team have mostly been working on getting the knowledge base up, like Sean said, trying to learn all the concepts because they all come way later in our class progression. So we've been working on learning a lot of digital signal processing concepts, the basics of software-defined radio, which is the main thing we're dealing with. So to do that, we were going to resources online. We went through an entire online course about software-defined radio, all to try and get the main goal is to write the software that will operate and will do the DSP, the digital signal processing here, so then we can transmit and receive from the ground station. And the other part of the team,
while they were doing that, the electrical engineering sophomore and myself were researching patch antennas. This is a patch antenna. So we want to do a 2x2 patch antenna array. Right now we're using Yagi-Uda antennas, which are directional. So they have a conical radiation pattern, meaning that you have to aim them at a very specific part of the sky to actually communicate with something. And we wanted a wider radiation pattern. So this has a hemispherical or close to hemispherical radiation pattern. You can more point and shoot, I guess, would be the proper term. Or not proper term, but I don't know what I'm doing for that. You can point and shoot. So, you can, kind of eyeball it more. So, and it has a wider bandwidth. So it would be able to handle the scientific data from the satellite vendor. So we're going to replace our downlink Yagi-Uda with the patch antenna so that it can take in these large data packets, scientific data packets. And then we're going to keep the uplink Yagi-Uda because it has higher gain, so less error in what it's sending. And so we're going to use that to send control signals. In reawakening ground station, last night we were able to actually talk to a satellite. This is telemetry from a
no weather satellite. It is very fuzzy because we were not, we had some kinks with using our main antennas, which would allow for better imagery. So I used a radio about the size of a USB thumbstick to get these. But we used satellite tracking software to account for Doppler shift, and we were able to download these photos here. Really cool. They come from sound files. So it downlinks as a radio wave, and then the antenna takes it in as a sound wave, and then it converts the sound to the signal.
Yeah, so as we said earlier, communications works a lot with the ground station as well. So if you think of this side as their antenna, this is like the ground station. This is our satellite. So here's what we're going to talk about today, which is our software-defined radio. This is a $20,000 piece of equipment here. So why it's so expensive is that when you take something very complex and you make it really small, like you need in a cube satellite, which has sizing requirements, it gets really expensive. So we are really blessed to have this donated to us as a club and to begin developing with it. So like he said, we have different tasks that we want to carry out with our satellite or ground station. So we want to send commands from our ground station to our satellite. Let's say we want to reorient our satellite so that our solar panels are aligned with the sun. We can do that by sending the signal from our ground station to our satellite antenna here and processing that command here on our software-defined radio. On the other side, we want to send research data from our satellite to our ground station. So we have a research payload on our satellite, and we'll modulate that data onto an analog signal, send it from our satellite down to our ground station. So what we've done as a communications group this year is work on simulating this communications link. So when you send something through a medium, so like between a certain distance, let's say, from our satellite to our ground station, it experiences a lot of noise and a lot of errors. And when you receive that signal, you need to correct for all those errors. So we simulated this in Python and then rewrote the script in C this year. So you guys will get started on explaining how that happens.
So the first part of our script deals with the creation of the data. So we first create the data with the pulse train, and then we'll create that data for transmission. As you can see in the red, the data is originally zeros and ones, and then we're going to remap it to ones and -1, which we can then send over to yeah. So once this pulse train is created, then it is pulse shaped. And basically what this does is it takes that pulse train and those discrete values, those -1s, and it just turns it into a continuous waveform. So to optimize transmission efficiency.
Yeah, so after those two processes, it's sent to our ground station radio and then sent to our satellite through the air where there's a bunch of noise. And when that happens, it distorts our data and it could give us something that we don't want. Like it can give like the wrong message. So the first process we do is called fractional delay. And basically the oscillators that create the frequency to send information in both of these radios will not be perfectly aligned. And so this accounts for that offset.
Right, so the next algorithm we run is called a clock recovery, and this is about synchronizing your transmitter and receiver to make sure that you're receiving your data properly. So next, like Rylan said, so you have two different systems that are existing separately from each other, and there's going to be small non-idealities in your system that makes different things just slightly different, which can cause a lot of errors in your data. So one of them is, if you think of a sinusoid, it has a certain frequency. So it's oscillating at a certain frequency. And the two systems might be creating a sine wave that is slightly different from the other. So you need to correct for that frequency difference on your receiver. And there's different algorithms to do that, and we run that algorithm. So if you look on the graph, you can see the red dots. We want to get rid of those. We want to squeeze those down to 0. And the red dots will introduce errors into your data. So by running these coarse frequency correction, and then if you click 2 more times, fine frequency correction, you can see that the red dots move closer to 0, and we're closer to recovering our actual data.
So whenever we send our data, we send it as real and imaginary numbers. And so through the air, when it goes through the atmosphere, right, our real numbers can become slightly more imaginary, which is not what we want. And so this IQ imbalance correction program basically helps eliminate those imaginary numbers as errors.
Okay, so then next we have our frame synchronization. So we start with a preamble, which is just a set of bits that we choose outside of data. And we use that and we cross-correlate it with our bits that are coming in. And then as you can see, once the preamble, which is that set of data, is matched with a coefficient, it creates a big spike. And that spike tells us where the preamble data ends and then the payload data begins.
And then after the beginning of this data is detected, basically it just undoes, or it's opposite of full strain, and it takes those ones and negative ones and turns them back into the 0 and 1 so we can recover the original data.
Yeah, and along with this, we have a cyclical redundancy check, which basically just makes sure that none of our data is corrupted.
So on our satellite, we'll have this small little radio, right? And that's what's shown in the gray box on the right, the SDR Linux computer. And on the left, we'll have a flight computer, so that'll handle all of our commands and movie motors and data from sensors, right? And then so the SDR will handle all of the communications. And so we need a way to talk between the flight computer and our small radio.
So we've been developing sockets, which basically allow the flight computer to communicate with the SDR so that the flight computer can take data from the sensors and then send it to the SDR where it gets processed, and then eventually it'll get sent back to the ground station.
And then so you can also see a bunch of services lined out there. And so we have a bunch of programs that are basically managed by these services. So we'll have a service that runs a transmit service, a receive service, a sort of server to handle all the data communication between the flight computer and the radio. And so we have services they're simple ones anyway, that can just run once and start up, or it can run just indefinitely. Every time the process ends, it'll restart it.
Yeah, so that's kind of our system's level design for what we plan on implementing on our actual hardware. So right now, everything that we have is contained within this simulation. And our next task is to split the simulation at where we simulate the transmission. So you have your pre-transmission, which would be your transmit service. So preparing your data to be sent over the data. And then you have your receive service, which is the other half of the simulation, which corrects for all those errors which are introduced between your two antennas. And now instead of simulating those errors which occur and those offsets that occur, we'll actually experience them between our two antennas based on the medium they're traveling through, how the antennas are polarized and matched and everything. So that's kind of the next step for the communication squad, implementing our scripts on the actual hardware and working with the Epic Solutions team who gave us that really fancy SDR to use the hardware. So it's been a lot of fun. Any questions? I think we have a couple minutes, right? 3 minutes. Any questions? Go ahead.
What has been your guys' favorite part of working on this project?
So all the graphs you saw earlier, that's all by signal processing data, or for processes that we do through the transmission, right, to correct for those errors. And so previously it was all written in Python, and so we've all been working the past, months, I guess, converting all that Python code into C. And so
I think it's been a really rewarding process to successfully do that. I also found it really fun and rewarding to work with our industry partners. So we have some people at Epic Solutions who really know what they're doing. Excuse me. And they were willing to Zoom in with us twice and give longer form discussions about how to actually do things and what's the best way to do things. And that's been really great for our development as engineers. So I really enjoyed that. I know it's kind of nerdy, but I'm kind of nerdy, so.
Why was it version Python?
Yeah, so there's this resource called PySDR. It's a software-defined radio textbook that basically walks you through what's the best way to build a digital signal processing simulation, and that's all written in Python. So that was just the easiest way to start. And then once we understood the requirements of our hardware, so our super fancy SDR right there runs totally on C, and its APIs are also written in C. So APIs are something that allow you to control certain parts of the hardware from your script. So since everything was written in C on that, we needed to transfer everything into C. It's also just a better language to use for something like this. You get a lot more control. Okay. If there's no more questions, anything lingering?
Any ground station questions?
There's previous ground station members in the room. Well, shout out to the city over there. Okay, so I think you guys are going to be heading. What's up? Go ahead.
So these antennas look like they were 50 years ago.
Right.
So
they were.
What makes has the technology changed on these?
Oh yeah. So so kind of how our design process works is these. What an antenna is it's literally just, you can use a wire if you want it. These work perfectly fine for prototyping, but once we get to the actual satellite, we have picked out certain antennas that we want to use that are much higher quality. So I think that we're going to be using something called a patch antenna, which looks kind of like this. It's just like literally a square of metal. And I think the one we picked out was $2,500. So they're like very precisely made and function a lot better than these ones. But when you're working at close distances, it doesn't matter. This is a great way to test. Good.
All right. We're going into the next station, which will be the next room over. Although I'm not supposed to have a bias, I kind of have to have a bias because this is the project I'm most involved in. So we're going to Iris. Yeah. So just follow
Starshade. There are two teams who want to do very exciting stuff.
And then slide it together. And so it's a super small, lightweight solution that takes very little power, and we can make this even smaller than it currently is.
And then it could be a lot smaller. We are able to shrink it a lot. It's a lot lighter than before. And then the big improvement that we made is that we can actually remove the shelf, so it's much easier to change and add things or remove things as we need them, which will help a lot when we're actually there and we need to make sure everything's working as it is.
We also launched a balloon and actually tested our system. It didn't work, long story short. It didn't deploy properly, but we still recovered it and got all the data back so we can learn from it and make improvements basically, so that way it will work when we do it in Antarctica. So here's a picture of the balloon launch. Yeah, there it goes. So we were able to recover that, and while it wasn't successful, we still got all the data. Here's the balloon path that it took. Here it is plotted over like an actual map, and this is what it looked like when we recovered it. So,
and we had a GoPro on there that's 360, so we can act like we're on the balloon or on the air system.
So yeah.
So had you preset for this launch this weekend? You preset a destination,
Yes.
and so it was trying to launch it to get to that destination, but it wouldn't release it. That would happen.
Right. Yeah, that's exactly what happened. So we ran a trajectory, like predict, and then selected targets as just like the centers of open fields around that predicted landing area. But it never got the chance to even steer because it never deployed.
So exactly what it's releasing.
Yeah. Any other, looks like we're pretty much out of time, but any other quick questions? Yeah.
Concerns with the Antarctic condition?
Yeah, so that's actually, that's a very good question. The Antarctic conditions are mostly only an issue because of the time that it will be out, like on the flight line. The temperature at this altitude is actually like negative 70 degrees Fahrenheit. So we already have designed the system for like very good thermal properties. That being said, it can always be better. So part of this new board is it's powered by different batteries that have like very good thermal characteristics. So yeah, definitely consideration.
Okay, we got to rotate the groups outside.
All right.
Thanks for coming. For the group in here, please follow me. I'll bring you downstairs to CubeSat.
Yeah, but let's both try it. Okay, so I don't really know. Because what I'm worried about happening then is that we take all the time. So you guys just go first.
Okay.
We just gotta get off the bus. Get off the Yeah, we get it.
All right, hi, so I'm Grace, I'm the lead for the Starshade project.
I'm Oriana Sally, I'm a freshman aerospace engineer.
And so we competed this past semester in the fall in NASA's Starshade Undergraduate Challenge, which I'm not kidding. I'll start by explaining what a Starshade is. Basically, it's just a big disk that sits out in space in front of the telescope, and it allows us to block the light from a star, which is our target, and then we can look at the things that are dimmer that would be circling around that star that would have otherwise been like washed out by that light. And so, as you can see, it starts really small and it has to deploy. So this is a really unique design challenge because it has to be really light to get off the ground, really small to get off the ground, but then it has to be really stiff once it's out deployed. So some of the design requirements for the challenge were that the Starshade had to be 100 meters wide, which makes it NASA's biggest Starshade design yet. It had to have 24 pedals, under 1,000 kilograms to get off the ground in like a affordable manner, and then stiff enough to withstand plus or minus 0.03 Gs, like in and out of the plane of the Starshade when it's moving in space. And then there you can kind of just see a little depiction of that small space that it needs to fit in when it's on the rocket, compared to the 100 meters that it actually is going to be when it's fully deployed.
Okay, so for our design, we took a simpler approach on the challenge, and we focused on 3 specific design features that are the robust deployment, the lightweight composite materials, and the self-supporting.
So starting with the deployment, when we take off, we're obviously, like I said, in that 2-meter package, and then in order to get out, we use inflatables, a web of inflatable tubes along that center circle to push the entire thing out. The entire center circle is folded in an origami pattern in order to stay small, and then those inflatables push out. The hinges lock into place, holding that circle into place, and then the pedals have these kind of like X trusses on them that extend outwards like that, and that pushes them out to their 25-meter thing.
Okay, so for the composite materials, we took aluminum in honeycomb shape. This way we reduce the weight of the material, and we had it in a way that it had a panel of carbon fiber below and up, and making a sandwich kind of shape. This shape allows the structure to be both lightweight and resistant. And we also use carbon fiber cables. We chose this because of its lightweight and also its tensile strength.
And so as Grace was talking about in the deployment of it, it has to start out very small and compact like origami shape. And so in order to achieve that, we knew that we couldn't have any stiff structures in that inner ring. And so to kind of get around this challenge, we use these inflatables, which obviously are bendable when they're not filled. But when we use the compressed gas, they'll push everything out, and then these the stiff arms, which are like the which make up the ring, they'll be pushed out, and then they'll lock into place with a locking hinge. And so then once those all out, there'll be a stiff inner ring to provide the structure for the pedals around it. And then to keep that ring in place with the bus, we have the carbon fiber cables coming from the top and the bottom of the bus at an angle, just to kind of keep them in tension back and forth so it's not floating up and down, it's staying centered on the bus. And so, yeah, go ahead. We submitted in December our whole project document, which is very long, a lot of documentation and calculations included with that, to the committee, along with our computer modeling of our design, as well as our images and videos of the actual design we created, actual model we created. And then in mid-January, we were told that we won first place and got the grand prize of $10,000. So it'll go into IrishSat for further research and development. But I think the best part was probably the cake we got from the exec board. So it was a good treat.
That's it.
Any questions?
Does it need to be retractable, or does it just like plug out?
So, no, I mean, technically, probably yes, for like the purposes of not having like tons of space trash and like being able to reuse it, but unfortunately, like a lot of space systems aren't really like thought of in that manner. And so that wasn't part of the design challenge. In fact, like, I would say the focus of this was definitely the structure once it was already out. Deployment was an interesting aspect of our design that helped us win, I think, but wasn't like the main focus of the competition.
So now we'll talk a little bit about Iris, which is our high altitude balloon project. So starting off with where we were last year's Banquet, if you guys were here. Basically, we had a rough system for this floating dragging design competition, which is a design competition that NASA put out to design a system that can deploy off of like a high altitude balloon at 120,000 feet. And just for reference, a plane, like a commercial plane, flies at like 30,000. So this is very, very high up there. And a lot of very interesting research is done at that altitude. So NASA needed a way of basically safely carrying hard drives of data from the balloon down to a safe place on the ground. So our system is designed to deploy off of the balloon and then completely autonomously steer to a target that's like predetermined as like a safe place to land. So last year we had a system that was very like a prototype, like, all right, like I think this will work. You know, we had rough things sketched out. This was what our electronics look like, and this is just half of them. And this is a first test of our system, which is we are steering using what's called a parafoil, which you see deployed right at the end here. And you can steer that by like pulling on the brake lines. But those have had issues with deploying at like very high altitudes where the density is very low. So we have this like first stage chute that comes out, and then from there it deploys the parafoil. So over the summer, we turned that rat's nest of electronics into a very nice board that has like all those connections on the board. And that's what you see in this like final system that in August, we went down to Fort Sumner and launched with NASA. This is just like a quick slide to kind of show, we had to go through a ton of documentation to be able to launch with NASA, including like a big structural analysis packet that we submitted and a big software design review, like running simulations demonstrating that our software works. But ultimately we went down to, we also did a test from a drone, so we could actually test the controls of the system. So this is the drone here. It's a nice fancy drone that we bought with our prize money for being a finalist. But there's the parafoil, and it's deployed, and it's actually steering itself right now, which is pretty cool to see that like our system that we had thought of actually works. But that's just from 400 feet. So we went down to Fort Sumner to do the real test with NASA. So Sarah's going to talk a little bit about that.
Yeah, so in August, we went down to Fort Sumner, right in the middle of the desert of New Mexico for 10 days. And we were supposed to launch on August 9th. We got there the 5th. So those first 4 days, we were really grinding to try to finish up the last few things that we had to do, adding a little bit of extra functionality since we had so much time. But we got the system really finalized, ready for launch. And we would go to the weather meetings and meetings with the FAA, with the NASA administrative team. And then finally, when launch time came around, they decided that they were going to repeal our ability to drop. So we'd still be able to go up on the balloon, but we couldn't drop off and steer down just because of some FAA paperwork issues. But so it launched on the Saturday after we left, and we got it back. And yeah, that picture is cool of me next to the actual gondola that they used to load up the balloon. It's a really big balloon.
Yeah. So to give like a sense of scale, this is the launch vehicle. This is Sarah, like smaller than the tire of it. Basically, the gondola, which is like the size of a car, hangs from here, and then the balloon attaches, and the balloon goes up from there. So here's a picture of it at launch. That's that same launch vehicle. This is the gondola with our system attached to it, like tiny right there. So this balloon, by the time it gets fully inflated at altitude, it's like taller than the Empire State Building. So these systems are massive, and a lot of very interesting research is done on them. A lot of telescopes are done because you get through most of the atmosphere, so you get very clear picture of the space without actually having to like time on, like you've heard of like the James Webb telescope or obviously the Hubble telescope. It takes a lot of time and money and energy to point those telescopes to where you want, like your particular research group wants to look at. So this is an alternative for that. You can basically launch them on a balloon. So because we didn't get a drop, the NASA, this is important enough to NASA that they essentially revamped the competition and relabeled it Ice Dragon because the finalists all have the opportunity to integrate with them in Texas this summer, and then they will launch our systems from Antarctica in January of 2025, which is very exciting. We basically got like another shot with NASA to develop the system. And we also got more funding, which is just like, there's 4 finalists now, and they gave each of us $10,000. So it goes to show like how important this technology is. When we were down there, Sarah overheard like them say like,
They basically, when we found out that they weren't gonna launch us anymore, some of the engineers were talking to each other like, shoot, like, what are we gonna do now? We're supposed to use this. Like, so this is something that they want to take and use for their own ballooning purposes.
And they also added a couple new requirements, which are basically based off of our system while we were down there, because they needed to like operate the system by themselves when we weren't there. So our system was extremely easy to use because everything is right on this like little panel mount here. So all they had to do is just like plug in a cable, like type in like one line of code to upload something, and then just like power it on. And it's completely ready to go now. Other student design teams had like very complicated launch procedures, and they had to like take a ton of things out and like screw things in and all that. So they added this requirement based on our system, which is pretty cool. So yeah, this year we did even more development. Sarah can talk about everything she did.
Yeah, so the system's pretty small as it is, but I thought we could make it smaller. And so all of the electronics you see currently inside of that prism is now on that board right there. And so all the processing, communications, everything can just be glued up right on there, and you can get rid of all of those boards that make that a little bit messy on the inside, and we can compact even smaller of a structure.
Because we're able to compact it, the system we made throughout this year is a lot lighter. It's a lot easier to use, and the biggest improvement we made is that you can actually remove the shelves from the module. So with this, if you wanted to access the shelves, you have to unscrew them and then get into the shelves. So what we did is we made it so now you can remove the shelves just by rolling them out of the main module, and then you can just access them directly if you wanted to change something, and then just slide them right back in.
So we made our system even easier to use, which is cool. So we also launched this system on a balloon this year, which was very exciting to actually, NASA wasn't going to do it for us. We were just like, well, we'll do it ourselves. So we launched a balloon. This is a video of launch. As we watch that, basically the system didn't deploy properly, so it never got the chance to even steer, which was definitely disappointing. But we were able to recover the balloon, or the system, and we have all of the data, and we also have some very cool GoPro footage. So here's a picture of where it was when we recovered it, and here's like our position plotted, which is kind of cool to see. But we also got like very cool GoPro footage that way we can like analyze the system and figure out try and figure out what went wrong. That way we can make it better for the next iteration. So here's the GoPro from 40,000 feet, and it's a 360 GoPro, so you can like look around.
Yeah, and Jack made a really cool connector so that it's basically the perfect position to be able to see anywhere on our system and the balloon. And we go over campus, so we'll view that too.
Any questions?
Is that the launch from like last week?
Yeah, this was last week, yeah.
Someone said earlier that the battery froze, is that correct?
On the GoPro, yeah, that's most likely. It stopped, that's like, this is our highest that we have, so we didn't get any of the burst or the descent. And that's likely because the GoPro just died because it got too cold, just like your phone dies when you go outside.
So it's not like you have to change the battery for the next flight to go higher.
We use the best battery that GoPro has for cold temperatures. At that point, it's gonna be just how do we insulate the GoPro itself?
Yeah, and you can also add an external battery, so it's just slap on a ton more batteries. And also the external batteries we can put inside the system where we have heaters and stuff. So we'll last long.
Thank you. Thank you.
Okay, guys, bringing you to your last station. Hopefully, you guys have been enjoying it till now. And yeah, we'll show you the.
I am so
Oh, I see my night. Just double check the structure.
You're good, don't worry. I don't want
Hello. Oh, no, I'm trying to downstairs. Oh, can you press the down button in the elevator?
Every year we cut it down.
You okay?
Okay. Yeah, do you know where you're going? Yeah.
So we actually got to think about this, thanks to our trusted industry partner, who has graciously provided us an SDR, a software defined radio. We're going to offload a lot of that signal processing to the SDR, whereas the flight computer's main computational tasks are actually going to be running the pulse filter and the attitude formation. Yeah, you guys might be strapped for also the SDR stuff. Great. So you guys will definitely highly recommend this 7.0 process. And you guys are going to be able to power this process. Just really like high process. Is it optimized for costs? I mean, it's not really optimized for anything. It's just kind of like, because that's your clients. I think we got, unfortunately, swap groups here. Going, okay, yeah. Okay. So, if you guys want to hang around for maybe a couple seconds and watch the actual reaction wheel spin a little bit. Tim, where are the batteries at? I swapped them. The new ones are 4.
I know. So they would be like,
Who's supposed to switch before? Also, who's
Say out of the world, you're live.
Thanks. That's all I needed. That's all I needed.
Thanks to the merchant.
I love the lyrics.
Yeah, Peter. The whole one for 3.2. Brilliant. I think they're running a lot. Yeah.
Those things
They've been lasting like quite well. We've been running 24 hours with no solar charge. Yeah, you can imagine. With heavy charges, I think you have a higher density battery.
What about May and Alexandra? What about you down there? Why?
All right, everybody. Thank you guys all for coming. We're your last rotation here. My name is Jackson O'Neill. I'm the head of the CubeSat project.
My name's Claudia. I'm the computing lead of IrishSat.
And my name is Peter. I'm the current power lead, future chief electrical engineer. Yeah. So our three teams and project groups are kind of combined into this one little demo session. So we'll start off with telling you a little bit about the CubeSat project. So the CubeSat project's entire purpose is to research, design, develop, test, and then finally refine all these subsystems required for a CubeSat operation in orbit. And a very large part of that is actually developing subsystems required in maintaining the payload. So as we can see on board here, this is our CubeSat, and this is our payload. It takes up a large part of it, so we have to make sure that all the systems on board are actually going to be supporting that payload.
And as for how we get this out into space, there's kind of two main programs that we dip our hands in this year and the following years. So first, there's NASA's CubeSat Launch Initiative, where you propose a mission to them, and if they like it, they'll launch it into space. There's also the University of Nagasaki program, which is run by the DoD, which kind of does a similar thing. You propose a mission, if they like it, you go to space. Kind of the main thing here, before you even start making these proposals, you have to decide what your mission is, which is determined by your payload. So that means that those students tag up with a professor who's doing some cool research on either novel technology, that's going to go into space, or some sort of novel science experiment that can only be done in space. Stuff like microgravity or growing biomaterial in space. So for this year, we worked with Dr. Chisholm and tried to integrate his novel antennas to go into space.
So yeah, Juwan mentioned Dr. Chisholm is a Notre Dame electrical engineering professor, and his research are novel antennas used eventually in similar to SpaceX's Starlink satellites, just CubeSat constellations providing internet. And then you might ask, what are those systems that are actually designed and supposed to support the whole payload and support the mission? First, we have power, right? How are we actually going to power every subsystem? We need to gain electricity from solar panels, store it in batteries, and then distribute it to all subsystems. Our ADCS systems, our Active Information Control System, how do we actually know which way we're pointing, know where we are in orbit, and then get to where we want to point for the specific task at hand, right? We want to point at the ground to downlink data. We want to point at the sun to charge our batteries. And how do we do that? Structures, obviously you can't just throw all this stuff out of the rocket. You have to have a box that actually contains it all. Our payload is the extending lens mechanism to go with the electrical engineering payloads, as you can see here. This lens will actually extend and retract to provide a certain level of gain for our antennas. Computing has to write all of the scripts to actually control all of these subsystems. And then finally, communications, right? We have all these awesome subsystems. We don't have communications to and from the CubeSat. It's all for naught.
Jackson already kind of touched on the structures.
Here's the actual structure itself, and here's the CAD model of how like what we originally thought of, and then it manifests in this. For this iteration, we use polycarbonate, which is clear plastic material. And that's kind of so you can see the inside systems. It makes for better viewing. But once we actually go up into space, we'll make all of our components aluminum. That way they'll fit the requirements of space. And then Jackson also touched on the payload. This right here. It's kind of like the main focus where we're really working all around the payload to make sure that all the systems feed in so that it can operate and do its job.
Yeah, right now we have it at we have a breadboard because we're going to do nano to actually power the servos and extend the lens up and down. We're actually going to replace that with a custom designed PCB for the real machine.
And the other components that are currently on the structure, the most important are the reaction wheels and vacuum torquers. And you're going to learn a little bit more about them in a couple of slides, but in essence, they control the satellite. And so we have one with the X, Y, and Z axis to allow for rotation in all of them, plus an additional reaction wheel that is 45 degrees from all three. So it can simulate movements in any of them and add in, make it so that if one motor fails, we aren't just lost floating in space. And then we also have a PCB stack, which is all of our software and essentially the computers on the satellites. And so we have those, and so each component of the PCB stack is situated near the components that needs to control.
Yes, there's a QR code up there for the purpose of this demonstration. You guys want to scan that? It's kind of cool.
Make sure you're on NDGS Wi-Fi.
Yeah, you're on NDGS Wi-Fi.
All right, so we just kind of talked about all the systems that needed power, and so our task was to find a way to make sure they can all get electricity. And yes, we will have batteries, so we can send out fully charged batteries into space, but eventually those batteries will run out. We need a way to charge them. Fortunately, it's not as easy as just plugging solar panels into batteries. That doesn't really work. Solar panels are kind of complicated. They require a little bit of tuning to make sure they accurately charge or can efficiently charge your batteries, and it should be powered. So that means we use this algorithm called the max power point tracking algorithm, which takes the most peak efficient voltage and current draws of the solar panels based on like how much sunlight are they getting and how much do we need to actually draw from them, and then maximize our power output. So we started developing a system that would do this on our own last year, and that was more difficult than we had imagined, especially since this year we have now researched and we use a Texas Instruments chip that does the computations of that algorithm for us, and we integrated it and custom built our own MPPT board that takes in power here, and then as well as outputs to batteries, and then outputs the power either from solar panels or the batteries to the system.
And the output of that first board goes into the bottom right picture, which is the second board, which is the power distribution board, which you might be holding now. It takes that one input and it distributes it to 5 separate subsystem outputs. So we have a Raspberry Pi flight computer, our motor board, our SDR and radio, and our payload antenna, and our heating system. All those are toggled on and off with I2C MOSFET switches, and we can monitor the actual power flow in each of those lines to see how much we're consuming in real time, virtually, remotely, and all over I2C.
Yes, it's the flight computer, piece of computer that. But then you can see there's a lot of, it's a huge computer and it takes a lot of data. So part of that data that it takes in is the I2C data from Maxim PowerPoint tracking chip right here. We actually have one right here live. And so if you go on that website, you can see live data from the solar panels right here. Like if you're actually on it, if I cover it, the solar panel will go down. There's batteries right here that are taking actual voltage from that. And then you can go further and see specific controls within the system. And so that's something that the flight computer can. We kind of leads into like the design constraints a little bit.
Yeah, so once we have these two boards completely functional, the next problem we're going to face is that those $40 boards would not last in outer space. So we have to research and test some new components that are actually space rated, which means they'll survive the extreme temperatures, the radiation, and the vibrations that the satellite will encounter in outer space.
This sheet right here is a stencil which we're going to use to actually paste on the solder for our 4th generation solar charging board, which is going to solve actual solar charging for the first time in our club history. So really exciting. That'll happen next week. Thank you.
Yeah, and now some more on the software side of things. This year, computing designed a full attitude determination control system. which is basically a system to determine how we're oriented, what our trajectory is, meaning where we're going to be going, and how we actually need to move our system in order to get back to our target. So if you look at our moving example right here, imagine the pink water bottle as our target state. When we move it away from the water bottle, it's going to, the motor starts spinning very fast up to its maximum speed in order to generate a torque to bring it back to the target. But it'll overshoot slightly, and it'll continue overshooting and trying to like adjust itself until it gets back to target. And that's basically our ADCS system. It's a continuous loop that tries to get us to the target.
So just like anyone, the CubeSat wakes up in a cold, dark void, and it's wondering, where am I? How does it tell where it is? It does so using an IMU, an inertial measurement unit, which contains a gyroscope, which can tell how fast it's spinning, an accelerometer, which can tell how its speed is changing, and a magnetometer, which can tell the Earth's magnetic field. And it can use that to tell where it is in the atmosphere so that we can pinpoint its location. It also has Hall sensors in the motors, which tell us how fast the motors are spinning. So with all of this, we pretty much have the full rundown of where our CubeSat is and what it's doing, but it's not always 100% accurate.
Yeah, so like Peyton said, sensors are usually important. However, alone, they're not much use because there's a lot of noise being in space. So we need to synthesize our physics equations of motion, which is basically predicting where we're going to be based on how fast we're currently moving and stuff like that. So bringing those two together is the unscented Kalman filter, which is a state estimation algorithm for a nonlinear system like our satellite. And so what this does is it takes sensor data and physics predictions and combines them to get a much more accurate view of our orientation and our speed.
So now that we know where we are and how we're moving, the CubeSat starts thinking, I'm here, but I'd rather be here. So if I'm pointing in this direction, I'm going to try and move in this direction. And the more I'm pointing in this direction, the more I'm going to move in this direction. That factors into our PD controller, which is a proportional derivative controller. The proportion part is what I just talked about. The farther you are away, the more you're going to push to get to where you want to be. The derivative part is the faster you're moving towards where you want to be, the more you're going to say, whoa, I better slow it down before I pass that point up. And using both of those, we're able to try and get back to where we want to go. And as you can see, a lot of the times it works decently well.
So there are two different types of actuators on our CubeSat. The main actuator is what's called a reaction wheel. Consists of a heavy disc of metal attached to a motor. By spinning that disc of metal, it's able to induce a torque that allows you to rotate along the axis of the motor. And then by having three of those, one in each major axis, you get 3D control. Now, one problem is that if those motors spin all the way to their maximum speed, but you're still moving, then how do you slow down further? For this, you need what are called magnetorquers. Magnetorquers are basically just coils of wire. You run a current through a coil of wire, produces a magnetic field. That magnetic field then interacts with the Earth's natural magnetic field, and that also produces a torque. And because that torque acts on the Earth's magnetic field, you're able to basically bleed rotational energy out of the satellite into the Earth's magnetic field, and then you can slow down your motors back to where they're usable.
The CubeSat knows where it is, but now we need to know where it is. So we made a simulation that allows us to input different torque values onto the three axes. And then from that, we can see how the CubeSat is going to rotate and what the rotor angle of the orientation is. And this can be used for future testing to improve the system.
So there's a lot of improvements we want to do in the future. One of the first ones is we just very recently got a new sensor, which will hopefully improve upon our current one. We also want to do a lot more hardware and software testing. Obviously, the more confident we can be in our results, the more confident we will be when we eventually send it into space. We also want to test out some potential new methods, for instance, multiplicative extended Kalman filter, which is a type of Kalman filter designed and used by NASA, which is supposed to potentially even be better than the unscented Kalman filter which we are using right now, as well as exploring other methods if we think we can make any further.
Well, I'd like to say thank you guys for all coming out to the banquet, and we'd like to open up this time for questions about anything you saw on the slides, any questions you might have for any of us, or anything you saw. What the Kalman filter is?
Yeah, so basically our sensor, one right here, it gives us information about what direction we're pointing and what speed we're going, but it's often like almost super wrong. It's really not great, this one specifically. So we have to bring in these complicated physics equations that can model what our satellite